Welcome to the second lecture of Module 3. The Module 3 is on equipment for gas liquid operations. So, in the previous lecture, we have classified the gas liquid equipments into two categories. One is the gas dispersed equipments and another one is liquid dispersed equipment. So, we have discussed in the previous lecture gas dispersed equipment. So, particularly we have discussed the agitated vessels, and we have also discussed the sparged vessels, and we have seen how to design the sparged vessel. And third equipment under gas dispersed conditions, we will discuss the tray column, tray or plate column. A tray column basically consists of two parts. One is vertical cylindrical cell, and second one is the tower internals. So, let us see the design as we have also discussed earlier in module 2, the gas absorption equipment. So, this is a cell where there is a liquid out at the bottom and at the top gas out. So, gas inlet in generally at the bottom, gas in, and you have liquid in at the top, so this liquid, there is a plate. This is the design for the sieve tray, we will discuss soon. So, these are the different holes on the sieve plate. So, this is the liquid in and this is where. So, this is the sieve tray, perforated hole, and there is a pool of liquid and the gas is going out from each tray and liquid coming down through the downcomer. So this is known as downcomer. These are weirs here, and these are different sieve trays. So this is a multi-tray towers, or we can get cascade system inside the tray towers, and there are nodules through which the liquid and gas are fed to the towers. So in each tray, the gas and the liquid are finely dispersed, and then the gas disengaged and flow through the upper tower, and the liquid flows through the downcomer and come to the down tray, lower to the tray. So this way the arrangement is counter current, and the contact of the liquid and gas stage wise, and overall it is a tower is cascade arrangement. Now the equilibrium stage for a particular tray towers required for a particular separation, or the ideal trays or equilibrium stage stages required for particular separation can be obtained from the material balance. Material balances and equilibrium consideration. So if we know the stage efficiency, then we can calculate the stage efficiency then we can calculate the number of real trays. So the number of real trays we can obtain if we know the stage efficiency, and this is obtained by mechanical design. So we will discuss the design part. So let us see the different parts of the column which we have discussed. What are their features? So first thing is the cell. It is generally made of metal or plastic materials. It It is selected based on the properties like corrosiveness of the fluid, temperature, pressure, and cost. The diameter of the tower is generally more than 1 meter in general, and it is up to 10 meters. There are trays. The tray serves the purpose of the intimate contact between the gas and liquid, and it acts as a stage. So, in each stage, the gas and liquid come into intimate contact, and so gas bubbles through the liquid and they come in intimate contact, and the liquid out from the tray and the gas out from that tray are in general it is in equilibrium. So, there are different type of tray used. One is bubble cap tray, and second type is the sieve tray, and third one is the valve tray. So, bubble cap tray this has two parts. One is this is the plate on which this is the cap and this is the riser, or we call chimney. Materials is made of low carbon steel, or stainless steel, or any other materials suitable for this purpose. The cap diameters are generally 1 to 5 inch dia bubble cap are any use. Now, another type of tray which is called sieve tray. It is the simplest type of tray. On the plate, it is perforated plate, and the perforations are usually the triangular shape peas are generally used. So this is the perforation hole. This hole diameter is generally 1/8 to half inch. These are very simple design and in common use. Another type of tray is the valve tray. The valve tray basically is a new class of design. And it can control the gas and liquid flow and liquid flow rate by appropriate opening of the valve. So these are proprietary items and not many designs are available. Design and information on its design are not available in the literature. Another important thing for the tray column design is the downcomers and weirs. So as we have seen, weirs. So this is a liquid inlet, we call liquid in, and this is known as the inlet weir. This is the outlet weir, and this is the downcomer. And this one is the seal, liquid seal. So downcomer basically is a passage through which the liquid flows down from one tray to the next tray. Below. And the depth wear, basically we use the wear this maintain a particular level of liquid on a tray, so that the gas bubbles through liquid and there is a intimate contact between the gas and the liquids. And the residence time of the contact between the gas and liquid time is maintained between 3 to 6 seconds. There are some nozzles and mist eliminator. Nozzles and mist eliminator. So nozzles are provided for the feed entry, gas and liquid, and there are different type of nozzle designs are available. And as we have seen, at the top of the column where the gas out, we have above the liquid inlet there is a little opening where when gases goes through the liquid, it takes away some of the mist which will form gas liquid contact in a particular tray, and that mist has to be eliminated. So there is a mist eliminator at the top of the column. So there are some operational problems in case of, or features in case of tray columns. So depending on the gas and liquid rate, if we plot gas rate and liquid rate, for a particular plate, if the gas rate is low and liquid rate is high, some of the liquid will channel or pass through the holes. In that case, we call it is weeping. So suppose this location M. So weeping. When liquid rate is high and gas rate is low, and then this reduces the efficiency of the column, reduces the efficiency of the tray, because there some of the liquid are not in intimate contact with the gas. Now, if there is excessive leakage, then we call it dumping. We call it dumping. So, this is the region we call weeping, and this is the region we call dumping. Now, if the gas rate is high, and liquid rate is low, in that case we have seen the gas takes away the mist or droplet of liquids, then we call it entrainment. So, the entrainment occurs when at this location entrainment, flooding, when both liquid and gas rate are very high. So, in that case we can see so this is the region of flooding. So, this is the region where we can operate the column. In this gas loaded region we can operate is the satisfactory region. So, another important thing of tray tower design is the turn down ratio. So, this is required to maintain the capacity of operations for a particular tower. Is depending on our requirement, we can increase or reduce the load or capacity of the plant. So, to make it flexibility, we defined a term is turn down ratio, which is equal to the design vapor throughput divided by the minimum operable throughput. Sieve tray generally have low turn down ratio is around 2, and in case of valve tray it is around 4. The tray spacing is an important requirement to operate the column successfully. More tray spacing more spacing is better for the space which will be provided for the gas to flow, and it is easy to operate, or the gas can disengage from the liquid droplets and get the free gas or saturated gas can enter into the next tray. So, larger spacing is better, but in this case if we provide large tray spacing is preferable, but increase tower height. So, there is a trade-off between the, and this tray spacing also related with the tower diameter. So, there is a trade-off between tower dia and tray spacing. So, we will discuss the recommended values for the tower diameter and the tray spacing in the design part, in the next design part of the tower. Now, we will discuss the design of tray columns. So, in a process plant, design, we need to know complete material and energy balance. For this we need the flow rate, composition of the gas and liquid, temperature, pressure, amount of heat input, output or generation, and also we need the physical properties like density, viscosity, diffusivity, surface tension, etc. So, with these values we can do the mechanical design calculations as well. As we discussed, there are three types of trays: bubble cap, sieve and valve. So, here we will discuss the design of sieve tray, which is very simple. Sieve tray design. So, the important part for the Sieve tray design, we need to know the diameter of the tower. Second thing, we need to know the tray gas pressure drop. Then size and layout of holes, tray spacing, downcomer and wears, and tray efficiency. So this we will discuss one by one. Let us consider how to design the diameter of a particular column. Tray diameter can be calculated based on the flooding considerations, and the Brown equation for flooding velocity can be written as V FL is equal to C SB rho L minus rho G by rho G to the power half. This is the superficial velocity at flooding. CSB, this is the Schroeder-Brown flooding constant. In general, this is not the constant, it depends on tray spacing, liquid load, hole area, on a tray, and hole diameter. So this CSB, the empirical constant, we can calculate CSB is equal to FST, capital F, HA and CF, where FST is equal to surface tension factor, which is equal to sigma L divided by 20 to the power 0.2. Sigma L is the surface tension, it is in dyne per centimeter. F is the foaming factor, which is equal to 1 for non-foaming, system, and equal to 0.75 or less for many observers. If HA is equal to 1 for AH by AA greater than equal to 1.0 and it is equal to 5 AH by AA plus 0.5 for AH by AA less than 0.1. So, AH by AA is equal to ratio of vapor whole area to the tray active area. And then we can calculate Cf is equal to alpha log 1 by m plus beta. Alpha is equal to 0.0744 TS. TS is the trace spacing plus 0.1173 and beta is 0.0304 TS plus 0.015 and m is equal to flow parameter which is equal to L dash by G dash into rho L by rho G to the power 0.5 and T S is the trace spacing in meter. If value of m is in the range of 0.01 to 0.1, then it is recommended that m can be used as 0.1 in the above equation. So then we can calculate the diameter of the tower as 4 Qg. Qg is the volumetric flow rate of the gas. F V FL into 1 minus AD by AT into pi to the power half. And it is suggested that AD by AT is equal to 0.1 for m less than equal to 0.1 is equal to 0.1 plus m minus 0.1 by 9 for m greater than equal to 0.1 and less than 1.0 and it will be 0.2 for m greater than equal to 1.0. Now, in most of the sieve tray, the holes are placed in a equilateral triangular pitch. So, this is the pitch length, and the diameter of each hole is say dh, then ah by aa we can write pi by 4 sin 60 dh by ph to the power square. So, it will be equal to 0.907 dh by ph square. Now, for downcomer geometry, we have said, so if this is the r is equal to dt by 2, and this is the length of the weir L WR, and this is the angle theta, and this is the height between the weir from the center of the tower. This is R WR. So, LR LWR is the weir length, AD as we said downspout area, tower cross sectional area, RWR is the distance of the weir from the center of the tower. Then we can write AD by AT is equal to theta minus sin theta by twice pi, and LWR by dt is the tower diameter is sin theta by 2, and RWR by dt is equal to half cos theta by 2. If the diameter calculated from the given equations is less than 60 centimeter, then generally stacked column may be in use. So, as we said, there is a relation between tower diameter and the tray spacing. So, dia dt in meter and spacing ts in meter. If it is 1 or less, then 0.5. If it is 1 to 3, then it is 0.6. If it is 3 to 4, then 0.75, and 4 to 8, it is generally 0.9. So these are the recommended values for the trace spacing and tower diameter. So the calculation procedure, it is an iterative procedure. First we have to guess TS, that is trace spacing, say 0.6 meter, and then calculate DT, tower diameter, and then check the value in the table for DT and TS, modify and repeat the calculation. To obtain new DT value, and then repeat this procedure until the convergence according to the recommended values in the table is achieved. So this iterative process has to be done unless we achieve the recommended value given in the table. So this we will discuss with an examples how to calculate by the iterative procedure in the next class. Thank you.